thanks everybody for coming here. We've got our next talks given by two speakers. We've got Lakshmi Narayana, a seasoned senior lead software engineer at Capital One, with focus on application modernization and leading transformative projects. He also brings a wealth of expertise in AWS technologies. Our second speaker, Ranjit Aneesh, who wrote the book on building distributed systems. It's actually a book, it's on Amazon. Please welcome both to the stage with their talk, Building Modern Distributed Systems with Advanced Integration Patterns on AWS.
Good morning, everyone. First of all, welcome and thank you for being here today. And thank you for the organizers for selecting such a beautiful venue. So we're thrilled to talk about building distributed systems leveraging AWS integration patterns. I'm Lakshmi Narayana. I'm a solutions architect at Capital One. I do have my co-speaker Ranjit here. If you want to introduce.
Hey, good morning. I'm Ranjit Aneesh. I'm a senior engineering manager at Capital One. Before Capital One, I was an engineering manager at AWS Lambda. I've also written a book on distributed systems called Building Distributed Systems. So, hi everyone.
All right, so given that the world is going at a really higher pace and cloud adoption is at a rapid pace now, building distribution systems is no longer optional, but rather it has become a foundational as part of your architecture. It could be like building for your scaling, or it could be building for your reliability, or building for your speed to the market as well, because the customer demands are on the other side is a lot more, and leveraging some of these modern integration patterns actually help us to build such resilient systems. All right, who we are, probably for those who don't know what Capital One is one of the leading bank in US. We have primarily our business into credit cards, auto loans, and also on the banking side. Even though it is a bank, it is built like a technology company. Tech is central for everything that we do at Capital One. We invest a lot on technology. We have almost 14,000 engineers working towards for a common goal. Changing banking for good is our theme that we work towards. We are probably the first bank get all into cloud. We took a bold step in 2016 that actually eventually went completely all into cloud. We also have many enterprise applications that we use to support our engineers. Given the scale that we have, 14,000 engineers, we don't want to do them a lot of mundane works. A lot of them things are automated, and also a lot of these tools are available. It could be enhancing your pipeline experience, or you have some common utilities. They are all grounded into common utilities. All right, this is our journey. So it's been almost a decade of journey that our transformation journey started back in 2014. We took a bold step hey, let's get API first approach. For those who might remember or recollect the SOAP world, and also how do we integrate systems. This was the first step to get to cloud, to APIs first. And we also contribute a lot to the open source. 2016, our CEO took a bold step. Let's get all into cloud. You can see that it almost took 4 years to get to cloud. It's a massive enterprise scaling applications. You can imagine how well it needs to be built. Given that it is bank, there is a lot of regulatory picture comes into picture here as well. So whatever we build needs to be built in a secured and well architected way. In between, we also automated and modernized our data ecosystem as well. Data is very, very crucial. And you can see some of the benefits that we are peeling out as we are enhancing our machine learning techniques as well. 2022, we launched Capital One software. We do have a couple of softwares that are available. One is Slingshot that will help you get insights from Snowflake. We recently released something called a data bot, which enhances all your tokenization aspect of it. 2025, we released 2 machine learning Gen AI use cases that are actually real now. We do have Auto Navigator, which is our application to support auto loans. We have created like best-in-class experience for our customers so that they can actually have a conversational AI to see what a user is expecting to buy and how we can relate it back to the dealers who are actually selling the cars and make that experience seamless. We also have another use case for our customer support agents to give like generative AI use cases coming in a much more enhanced way so that they can support the customers in an efficient way. Want to learn about Capital One? I mean, look at there are a lot of tech blogs available. We do a lot more careers as well. Talk to us if you need anything related to Capital One. All right, let's drill into agenda today. Like we'll be talking about like journey towards distributed systems in a complex enterprise environment. What are the integration patterns that are available? Given that, I think we are focusing a lot more on the AWS as cloud. There are a lot many providers available as well, but Capital One's house was like get all into AWS, so our topic will be mostly onto AWS world. As we adopted these integration patterns, what are the best practices that you can follow, and also like how do you adopt it at scale, given that the large scale enterprise company that we have enhanced our integration journey towards. With that said, I'll hand it over to Ranjit, who is going to talk about the first few slides.
Hey, hello again. So, okay. So, to get started, let's look at something that most of us may be familiar with, monolith applications. Before distributed systems, initially we used to have applications which were built as a single unit. The applications would have three main parts. They would have a client-side user interface. They would have a backend, monolithic backend application, as well as a database which has tables, usually RDBMS. And these applications would work with the monolithic backend, making sure to take the requests from the client-side user interface, do some business processing logic, update the tables, when a request comes to retrieve something, read the table, generate an HTML page, send it to the browser. So these were simple to develop. However, over time, as complexity of the applications would increase, it would be difficult for them to maintain a modular structure of the application. That would cause the internal modular structure within components to get disturbed and make them a maintenance nightmare. The changes are tied together, and so whenever you have to deploy the application, even if the change is small in one component, you have to rebuild the whole application and create a new version and then deploy that application to production. If a single instance is not able to scale with the coming traffic, usually what you would do, you will create clones of that instance, put it into the multiple servers, run a load balancer on top of that, so that you are able to suffice the traffic. If any particular one component fails, it can bring down the whole application down. Suppose there is an out-of-memory error at one place, can bring the whole application down. So those are some issues with monolith applications. Now coming to distributed systems, organizations who design systems are constrained to produce designs which are copies of the communication structures of these organizations. What that means is eventually when monolith applications are built, they are built across functional teams where those teams focus on a particular technology. They focus on UI, backend, or they focus on the database layer. And eventually, monolith applications end up being projects rather than products. The microservices or distributed systems philosophy is totally different. The focus is on creating services which are business capabilities. And when you run applications, you want teams to focus on those business capabilities who bring in domain strength in those areas. and these teams are cross-functional. They have experience on on the user experience side, on the back-end processing, database, and they're self-organized agile teams. So in distributed systems, microservices play a great role. And the focus for these services, as I mentioned, is the business capability. The focus is only on the business domain. An application is composed of multiple microservices or multiple of these business capabilities composed together to suffice the requirement of the application that is being built. Each service runs in its own instance, in its own OS process, so they can be deployed independent of each other through automated deployment pipelines. So if I have to update a business capability in one service, I don't need a complete new version of the whole application. There is actually no single version of the application. It's composed of multiple services. So what are the advantages that come with these distributed systems? They are highly scalable and available. That is because each service scales independently. And when they scale independently, it is easier to take in user requests for specific traffic that would be coming for those services. They are highly available because if a particular service is down, that doesn't necessarily mean that the whole application is itself down. Application can still run with a degraded capabilities. Teams are more agile because now you are being able to ship features faster because you're not waiting for that single deployment of the whole application. You have your service, you deploy features onto that service, and the automated deployment pipeline takes it to production. Eventually, you also have polyglot design in your implementation. So my particular service might have a specific requirement, and I can use any technology that I'd wish to, and I'm not constrained by what the application itself is about. Each service can choose its own application, and that is the beauty that comes with these distributed systems. Given that all these services are spread out, and there's no single runtime, a request may have to go through multiple different services, and observability becomes a challenge. You may end up with silent failures, so you need to really invest in your observability. You need a strong telemetry or telemetrics, dashboards, alerts to ensure that there are no silent failures. All these come with a cultural shift that is needed in your organization, in the sense your teams are cross-functional, and they need to also deploy the application that they are building. The philosophy here is you build, you run it. So you need to ensure that your team has those capabilities, and obviously that needs engineering talent. Now let's look at a particular case study of an e-commerce application which we want to disintegrate into a distributed system. Suppose you had an e-commerce application which have these 5 different services. It's a rudimentary, just a mini case study here. And if I have to split these components in my monolith, I could do that. Some of these services could be owned by specific teams who manage these services. I could have one service for the catalog, one for user service, and another for shipping, which are all disparate and actually are different business capabilities. So let's look at 2 specific services here, which have 2 varied and disparate requirements. In an e-commerce application, I may have a catalog service whose job is to display to the user when they land, the items in the inventory that is available. And that service is a read-heavy service. And I don't need it to be highly consistent. It can be eventually consistent. What that means is, if a new item is added into the inventory, I don't want it to be available immediately. It can take some time, and not necessarily at the same time across geographies. However, an order service, the primary job of the order service is to create orders. So which is a write-heavy service. But I also want it to be highly consistent because I don't want my users to inadvertently create duplicate orders when they are using the internet. So with that said, let's look at how I can deploy that on an AWS environment. If you look at from the left, when a user lands on an e-commerce platform, the first thing that they see is the list of items that is most of the time tailor-made for them through some recommendation service. But we'll not talk about those things. We'll keep it specific to our catalog service and order service as part of this case study. The user will first see a landing page, which will list down all the items. So the landing page itself has static images. It has some HTML for which, and if it is across the globe available, I want it to be very quick. So I could put a content delivery network service called a CloudFront from AWS, whose job is to, CloudFront is a content delivery network, which is basically a fancy edge server fleet. An edge server is one where a server is placed across densely populated areas to help cache frequently used, frequently visited sites from that area. My catalog service could be a Lambda, which will be able to serve all these different items that are there available on the landing page of the e-commerce application. If there is a shoe with different images, my catalog service could store that in an object store like S3 and cache that image in the Elastic Cache, which is available through the API gateway via the CloudFront. Why do I have an API gateway here? And that is because my API gateway acts as an abstraction over all my services behind the scenes. My users don't need to know about these services residing behind. All they see is a URL, but the URL has all the information to know where to go. On the other hand, the order service could just talk to the DynamoDB and with a strongly consistent reads and writes and ensure that there are no duplicates of the orders. With that, I hand it over to Lakshmi to go and talk about the integration patterns.
All right. Thanks, Ranjit. Now that we have established an importance of integration in distributed systems, here are like some of the popular AWS integration patterns that are available. I will deep dive each of one, when to use, what are the pros and cons of it. Like we'll go with synchronous integration, asynchronous, and orchestration. These are all the primary categories that I put in, which is like widely used. Let's focus on synchronous integration. So as Ranjit was pointing out, like, hey, typical e-commerce application, someone is placing an order, the user needs to be responded quickly, like given that the order has been placed successful or not. Like, so this is a classic use case when you to use synchronous integration, meaning here like you have a service A, which is sending a request to service B, and service A is waiting for the response to come back so that respondent can be on the user interface. Typical set of services that we have is like API gateway, and then you have your Lambda, which could be any other computing layer as well. It could be EC2 or it could be ECS. And then you have your dependent API calls that are available to make the call. Even though it works for some of the use cases, but probably doesn't fit. Like it has its own set of challenges. The number one thing is like tight coupling. Given that now service A is dependent corely on service B, if something happens on service B, then basically your overall experience has been hammered. It comes with performance bottlenecks because now your service A is depending on service B. If service B is like not performing that well, now you're having a bad user experience. Obviously, your failures has been cascaded from your downstream to your upstream, not giving best-in-class experience to the users. And also you have scaling concerns because now you need to consider all the scaling patterns that are available because now you have a mix of APIs that needs to scale accordingly. But it has its own use cases as well, where it fits in some of the use cases, like where I want my real-time interactions to be crucial. Again, the same example, user places an order, expecting a response back, that whether the order has been successfully placed or not. In that case, probably you should consider using synchronous communication, and also where your user experience is on high demand. Like, I mean, you're expecting like immediate feedback to be sent to the users. And also ensure that your overall complexity is minimal here, like your number of dependent calls are also reduced. Then you can leverage synchronous communication. With that said, I'll move on to the asynchronous integration. Again, this is another pattern which acts as a decoupled way of doing things. The same example that we saw in like service A talking to service B, but here we'll have some sort of intermediary, which could be a messaging system or it could be an event bus, basically decoupling the whole integration pattern. Unlike synchronous communication, asynchronous allows us a service to initiate a request, but without waiting for immediate response. The popular ones are SQS, like it's a queuing mechanism here. The other two are like really a pub/sub model, where I'm publishing a message and I have my integration patterns listening to those messages. And also have some sort of like real integration with streaming of data. So typical flows here, like the first one that I talked about on the SQS is point-to-point again. Like service A interacts with service B, but with a queue in between. Take an example again, an order has been placed successfully, but now a fulfillment service needs to consider this message and actually start shipping that order that has been placed. So here the order service puts a message into queue, and the fulfillment service just picks it up and processes it. There might be a lot of other examples, like where I want to publish this message to many consumers. Like here you can see it's point-to-point. If you want to fan out and have this broadcast this message for many consumers, the next two are the beneficial ones, like using SNS and EventBridge. Basically, the consumer, the publisher of the message just publishes the message into a bus or a topic here, and then you have one or more customers that listens to it and then process it. Again, the same example on the e-commerce website, when someone places an order, I want my fulfillment service to pick it up, and also I want my notification service as well to respond, and also my shipping label needs to be created. Now you have like 3 different variant of services that needs to act, but with a simple subscription of an event. The other benefit by leveraging EventBridge is like it has some more advancements, like we can apply rules to it now, and I can actually transform the data that is coming in the message. When I say rules, like let's say an example, like I want to listen to the events where I want to do like fraud detection. Let's see if their orders are coming from the same IP or from the same customer. I want to tackle that. This is a rule that you are applying. Rather than creating that rule in the code, you can just simply enhance the EventBridge service that is given by AWS. Listen for those events which are crucial for you for detecting your fraud techniques. And also you can transform the data that is coming in. There could be transformations that needs to happen so that you can apply it to your downstream, which could be even SaaS applications. The next one is streaming again. Like when the e-commerce applications like generate really large volumes of data, now you have many producers of the data, and you have many consumers of the data as well on the other side, which are publishing events, which could be like user activity that is coming from your user interface, or it could be click streams, or you want to ship this data to some open search and apply machine learning techniques on it. Like, now, given that the vast amount of data that comes in here, streaming probably a better use case for that scenario where you are actually broadcasting many multi-consumer events and multi-publisher events. It's been built like really for really high durable, highly scalable, and highly throughput transaction-based integrations. All right, what are some of the benefits that we see with the asynchronous patterns? One is scalability, given that now we have decoupled the systems. Each service can scale independently. And you can also allocate your resource allocation for varying payloads. Loosely coupled, again, like given that it's decoupled now, it's easy to maintain the code. Like independent teams can ship their code very easily, maintain their versions, simplify the overall communication. Modularity, again, like given the nature of like event-driven architecture, it allows teams to deploy, update the components independently, leading to a faster iteration and speed to market and innovation. Fault tolerance, given that these are all decoupled nature and it directly doesn't impact if one of the dependent services is down, because you can always retry and read it from your messaging bus or queues. This isolation really helps to have like resilience architecture and fault tolerance built in. Responsiveness, again, consider these are like different use cases. If you don't need like immediate responses to be happening to your customers, maybe in an asynchronous manner, could be like a pizza tracker system. Like I placed an order, but I'm getting the responses back from the real world. And also like the overall reduction of the cost as well, because now you're using resource in an efficient way. Reduce the overall development cost and also your infrastructure cost too. All right, I'll switch on to the next one, the orchestration, which is basically a workflow management using step functions. As your system grows, there's a need for coordination of these services, and it's really becomes crucial because now you need to understand the overall system. Again, consider going back to the same e-commerce system. Let's say I'm doing a return now on a particular order that I placed. Return have like sequence of steps, like whether the product that I'm returning is eligible for the return window or not, whether the product itself is eligible for the return, generating a shipping label, processing a refund, sending a notification to the users. These are all like sequence of steps that needs to happen. If you need to choreograph this in a right way, it's basically end up in a typical workflow where you have one-to-many or many-to-many transaction basis. Step functions comes at really heavy here. Like we can have built-in workflows with a clear workflow designs and also retry mechanisms that can be built in very easily. All right, I think we have seen these integration patterns. The overall benefits that we see is like, if at all you're trying to build a really high availability and high scalable and high reliable application, consider leveraging these patterns, because you don't need to invest a lot on this because these services are built for that purpose. And again, obviously, scaling is very crucial, given that some of the large enterprise applications that we handle at Capital One has significantly high volume of data that comes in. We need to be prepared for it. So having these services really helped us to change the game. And cost reduction is crucial. Like we need to think about serverless architecture a lot. And most of the services that we said, like they are all built for serverless in nature. Again, your development speed is super consideration here. Like you want to go faster, you want to build features fastly and release it to the customers. Having these integration patterns like really help us to achieve that. All right, what are some of the best practices and key takeaways that we learned at Capital One? So think about all these patterns. Don't consider it like late in the game, but start early during your design phase or architectural phase. And also think about design it for failures. Like it's okay to start like that. Assume that every integration fails, and see how we can actually build a fault resilient system, which could be self-healing. Build for resiliency at every point, which is very crucial. Like mimic your disaster recovery behaviors at every services that you use. It could be Lambdas or it could be any other compute services. Standardized patterns, like as you are scaling up at your organization, creating reusable patterns will really help. It could be your pipeline or it could be some of your code reusable libraries, pattern as a code. Make sure they are all available, discoverable to all your engineers so that they can leverage. And also document your decisions. Ensure which service to use for which use case is very, very crucial so that the engineers doesn't mix up, use the wrong choice. Right-sizing the solution again, understand the business complexity, then tie back to the need that you need to do for the integration service. Integration, consider a lot of operational overheads. Sometimes you don't need mission critical service to be there, or it could be less friendly user interface that is needed. Consider all these choices when you are building any application. Evolve gradually. There are a lot of services that are available from AWS. Make sure that you consider the use case and also its user's pattern in a right way. Try it out, test it out. If it works, document it, leverage it, and make sure that it works for your backward compatibility as well. How did we scale at Capital One? We formed a lot of these community of practices for different streams. It could be one for serverless, one for your data community of practice, and it could be for your Gen AI. What these community of foundation do is they initially does a lot of POCs, govern the structure, create documentation, create best practices, which really help to scale well. The core pieces document your standards, which could be leveraging different patterns, when to use which service, build usable templates. This is something really helped us shape us. We built a lot of we automated bunch of our CI/CD models by leveraging reusable components. We also have tons of libraries that we say patterns as a code that a lot of our engineers are using it to go faster. Scale with training. Again, there is no way that you can scale without training. Make sure you have good documentation, have self-servicing needs, and have good formal transition to scale at the company. All right, this is the end. Thank you all again. If there are any questions, we're happy to take it. If you need any questions about Capital One, feel free to tap us.
Should I say it?
Yeah, go ahead.
Sure. Maybe that one.
Oh.
I'm just going to sit down here. Thank you very much for your talk. I am wondering when it's too much microservices, and have you experienced the pain of maybe coming back to monoliths at some sort?
So I think we apply a principle called build your microservices with a business domain-driven one. So we just don't build one for notification service, hey, one for my Slack notifications, one for my email. Have some sort of boundary considered on the top, hey, notification as a purpose is my thing to solve. So we put that boundary as the top one. Within that, you can have multiple routes coming into different business use cases. We don't want to build too much granular, and we don't want too much too much monolith as well. You need to consider that sweet spot. One thing that really helped us is understanding your business domain. We don't want to crisscross credit card driven APIs to auto loan APIs. There could be some common theming that comes in. That could be, hey, all customer related data can sit in one microservice. Again, these are huge. Again, you need to put that lens as well when you are designing or architecting your microservices.
I would like to add to that. So one rule of thumb, or you say one way you could think about it is your application, what are your core areas of business capabilities that it has. And suppose you have a transactional system versus a non-transactional, eventually consistent systems. It's important to make those divisions and identify those trade-offs before you think about microservices or monolith. Not to say that monoliths are bad or everything is made for a specific reason. So consider a banking solution which is online transaction processing, highly consistent, and many different systems which have to be working in tandem. If you split them, it will be easy to deploy, and it will be easy for some capabilities that they offer, but at the same time, now you will add a lot of latency to it because they have to interact with each other. They are not running in the same runtime. So this is important to consider that, what are your trade-offs, what you can live with and what you cannot live without. So before you make any judgment around that.
Any other questions?
Yeah.
Hi. So my team currently is having a transition from a monolith service into a microservices architecture. The way we're going about doing that is we're starting out